x value of a, then f is continuous at that same x value of a. All right. Now, this theorem is an if-then statement. It's a conditional statement. We have our if portion, our antecedent is, or our hypothesis is f is differentiable at a, and our conclusion is f is continuous at a. So if I hold a function behind my back, and I've got this function hidden behind my back you can't see, and I tell you the function I'm holding behind my back is differentiable, then you can immediately say, ha! I know that that function is continuous. I know that I will never have to lift up my pencil when I want to draw this function. On the other hand, and so I pull it out and I say, yeah, you're right, that function is continuous. Now, I take another function off my paper, and I hold that one behind my back, and I say, the function behind my back is continuous. Can you immediately say, ooh, I know that that function is differentiable? No, that would be the converse of this statement. And so the converse, and here's a warning, the converse of our theorem, meaning if f is continuous at a, then f is differentiable. This is completely and utterly invalid. If I tell you that the function behind my back is continuous, you don't know nothing about whether it's differentiable or not. The function I'm holding behind my back could be y equals absolute value of x. Y equals absolute value of x is continuous, but is not differentiable at x is equal to 0. All right, so if our function f is differentiable, then our function f is continuous, but the converse is not necessarily true. And I really like these theorems, these if-then kind of theorems, and what happens if you flip them around. So this seems like a really good example of, can you draw a picture, so a test question of, can you draw a picture of a function that is differentiable but is not continuous? And you'd say, no, not going to happen. But can you draw a picture of a function that is continuous but not differentiable? Yes, you could draw a picture of y equals absolute value of x. Okay, any questions about that?
So you don't mind me asking, I was following along with that, I completely lost the explanation. What is differentiable again?
So differentiable means that a function is smooth. There's no cusps, no corners, no kinks in the graph. So the two words, the conceptual version of our words, continuous is you can trace the curve with your pencil without lifting it up. Now we have a definition of continuous, a limit definition, rigorous definition, but the conceptual idea is trace the curve without lifting your pencil. Differentiable, the rigorous definition is that our derivative exists at the particular point we're interested in. The conceptual idea is a function is differentiable as long as it doesn't have any cusps or corners, discontinuities, or vertical tangents. Okay, other questions or comments? All right, in that case, I would like to wrap up today with one final example.